Okay, so now in 8.12 we are going on to systems of many interacting objects. Remember in 8.11 we looked at systems of two interacting objects. And essentially what we found there was, let's see if we can go back, we found two main things, okay? The first thing was that even if you have the objects inside your system interacting with each other, exerting forces on each other, if those two objects are inside the system, those two forces are internal and they cancel out. And so the only force that changes the momentum, the time rate of change of the momentum of the system is the external force. So you need to be able to identify what is external, what forces are external and what forces are internal to the system. So that's the first thing. Only the external forces changed the momentum, okay, with respect to time. And the second thing is that we were able then to, if we knew the external force and we knew the sum of all the inertia of the system, we could calculate the acceleration of the center of mass of the system. We weren't necessarily able to calculate the acceleration of the individual objects, but we could calculate the acceleration of the center of mass. And that was simply equal to the external force divided by the total mass. Okay, now 8.12 is pretty much the same thing. You can go through this, but the conclusion is the same. That all internal forces add up to 0. If you've got not only two objects, but three objects interacting, or 4, or 100, or 10 million, if they're inside the system, then the forces that they exert on each other are all internal, and they add up to 0. So, the time rate of change of the momentum for a system is then simply equal to the sum of the external forces. Again, please make sure that you know how to identify what is external and what is internal. Okay? Then, again, in a similar way to the two-object system, the sum of the external forces is equal to the mass times the acceleration of the center of mass. So if you want to determine the acceleration of the center of mass of your system, we sum up all the external forces and we divide by the total inertia of the system. Okay? So let's see, I haven't really prepared on this, but let's see if I can. Seems that my computer is a bit slow. Okay, so let us. So if we've got, say, a few objects interacting here, okay, so object 1, 2, and 3. Is that a 3? A 3, okay. And that is our system. And we have an external force there, external. Okay. Then if we take a look at 1, what are the forces acting on 1? The only force acting on 1 is F2 on 1. Okay? What are the forces acting on 2? They're going to be F1 on 2. Okay, so that's F of 1 on 2. And we're going to have F3 on 2. Do you see that? So this one is going to experience a force from 3 and from 1. And then what about 3? We're going to have F external, and we're going to have F2 on 3. Okay? So, if you add up, if you're summing up all the forces, you're going to get, for this that's acting over here, you're going to get, I'm not going to go through it all. You're going to get this one, F21 plus F12 plus F32 plus F23 plus F external. Okay? And we know that this is the opposite of that. This is the opposite of that. So these ones cancel. And so the sum of the forces is simply then equal to F external. And this is the only force that changes the momentum with respect to time. Okay? All right. Now, so that's hopefully that helps. And then the other thing is that the acceleration of the center of mass is then equal to the sum of the external forces, okay? So, in the same way with this system, even though you've got three objects interacting, moving within the system, somewhere there is a center of mass, okay? Somewhere in the system there's a center of mass, and the acceleration of this point is equal to the external force, or if there's more than one external force, the sum of these external forces divided by the total inertia, m1 plus m2 plus m3. Okay? Is there anything else I want to say? Oh, and the basic idea is that it is as if all of this inertia is concentrated right there. The inertia of 1, 2, and 3, if you add them up together, it is as if all the inertia is concentrated at this point, and all the external forces are being applied to this point. It's very similar to if you have a single object, just a single object, and you've got these external forces being applied to it. Okay? Again, the acceleration of that object is equal to F over m. The mass of that object, or the inertia of that object, and so the acceleration is the forces applied to that object divided by the inertia. Well, in the same way, if you have a system, the similar thing happens to the center of mass. So I hope that you can see how these are similar. For a single object, it's very easy to understand, but for multiple objects, the same idea happens, but it's to the center of mass. Okay? See you in the next video.